morning everyone. So today we are going to discuss the last topic of this chapter, which is inverse of linear transformation. So recall the definition of range of T, which consists of all images under T of vectors in V when T is a linear transformation from V to W, and T is 1 1 if each vector in range of T is an image of unique vector V in capital V. And because of this uniqueness, we can talk of the inverse. So we define T inverse from W to V or from range of T to V if T is 1 1. So if T is 1 1 on 2, we define T inverse from W to V, because in that case R of T is equal to W. Otherwise, if T is 1 1, then also we can define T inverse not from W to V but from range of T to V. So let's see this exercise where we need to find the T inverse if it exists. To show that it exists, first we need to show that kernel T is equal to 0. So if I compute kernel T, then it is all those x, y, z for which T of x, y, z is the 0 vector of 0 plus 0t plus 0 t square. And this means that all those x, y, z for which you will get x is equal to 0, then x plus y minus z is equal to 0 and x plus y plus z is equal to 0. Solving this, you will get x is equal to 0, y is equal to 0 and z is equal to 0. This implies T is 1 1. Since T is 1 1, we can define T inverse from R of T to R cube. But it is also interesting to observe from the rank nullity theorem that the dimension of range T is 3 and the dimension of P2 is also 3, and therefore the given linear transformation is onto. In that case, we can define T inverse from P2 to R cube. So this is how it is defined. T inverse of A plus BT plus CT square is equal to XYZ, where XYZ are unknown and we need to find their values. So this is same as T of XYZ is A plus BT plus CT square. Now we have already given the value of T of XYZ. We substitute the value, compare the coefficient on both the sides, and that gives us the values of XYZ as follows. Once we have the values of XYZ, the T inverse can be computed like this. Moving further, let T from P2 to R cube be a linear transformation, which is defined as follows. The first step is to find T of x square plus 5x plus 6. So this is same as P of minus 1. So if I substitute minus 1 here, this becomes 1 minus 5 plus 6, which is 2. Then P of 0, this gives you 6, and P of 1, which is 5 plus 6 plus 6, which is 12. So this is my required T of x square plus 5x plus 6. Next is to show that T is 1 to 1. For this, I need to find the kernel T. So kernel T is A plus bx plus cx square such that P of minus 1, so this is my P of x, such that P of minus 1 is equal to 0, P of 0 is equal to 0 and P of 1 is equal to 0. Now P of 0 is equal to 0 gives you A is equal to 0, because you need to substitute x is equal to 0. Now P of minus 1 is equal to 0 gives me minus B plus C. So C minus B is equal to 0, and P of 1 gives you C plus B is equal to 0. Solving them gives you B is equal to C is equal to 0. This means the kernel T is 0 polynomial, 0 plus 0x plus 0x square. This means t is 1 to 1. Next is to find t inverse of 0, 3, 0. So t of p of x is p of minus 1, p of 0 and p of 1. This means t inverse of p of minus 1, p of 0 and p of 1 we need to find, which means that we have given p of minus 1 is equal to 0, p of 0 is equal to 3 and p of 1 is equal to 0. So p of 0, so if p of x is ax square plus bx plus c, then p of 0 is c, so this means c is equal to 3. Now p of minus 1 is a minus b plus c, which is a minus b plus 3, and this is equal to 0. P of 1 is equal to a plus b plus 3 is equal to 0. If I add these two, then I will get 2a is equal to 6. That gives me a is equal to 3. If I substitute a is equal to 3, so substituting a is equal to 3 gives me 3 minus b plus 3 is equal to 0. That gives you b is equal to 6. So solving this, we will have a is equal to 3, c is equal to 3 and b is equal to 6. It means t inverse of 0, 3, 0 is equal to ax square, which is 3x square plus 6x plus 3. Okay, so quite interesting. You can see that how we have approached. We have considered p of minus 1 is equal to 0. So minus 1 means a minus b plus c is equal to 0. P of 1 is equal to 0, a plus b plus c is equal to 0. And p of 0 is equal to 3. That gives you c is equal to 3. Substituting the values, we will get a minus b plus 3 is equal to 0, a plus b plus 3 is equal to 0. When you add them, you get 2a plus 6. So 2a is equal to minus 6. That gives you a is equal to minus 3. Now substituting a is equal to minus 3. So minus 3 minus b plus 3 is equal to 0. That gives you b is equal to 0. So sometimes it may happen that you do a very small calculation mistake, and therefore t inverse of 0, 3, 0 is ax square, which is minus 3x square plus 3. Okay, let's move further. Next is the composition of two transformation, which works same as we define the composition of two functions. So t of t1 u is same as t2 and t1 of u, and it's very easy to verify that t2 of t1 always forms a linear transformation. Let's quickly try to compute t2 of t1. So t2 of t1 ax square plus bx plus c is same as t2 of t1 ax square plus bx plus c, which is t2 of 2ax plus b. Now this is how t2 is defined. So it is taking c to 0. So it will take means the constant to 0. So b would be 0, and it is taking bx to bx. So t2 of 2ax plus b becomes 2ax. So this is T2 of T1. Similarly, please do try to compute T1 of T2 by yourself, and you will observe that they are unequal. At the same time, if you try this exercise, they comes out to be equal. So this is the last result, which shows that if T1 T2 are 1 to 1 linear transformation, then T2 of T1 is also a linear transformation. So to prove it, you can consider T2 of T1 u is equal to T2 of T1v, and we have to show u is equal to v. So this becomes T2 and T1 of u is equal to T2 and T1 of v. Now T2 is 1 1 implies T1u is equal to T1v. Again T1 is 1 1 implies u is equal to v, implies T2 of T1 is 1 1. Yes, similarly it's very easy to prove the other result also. You start with left hand side and you may reach to the right hand side. So that's all from this chapter. In the next class we will start a new chapter. Thank you very much.